Hello everyone, today we're going to talk about matrix completion for collaborative filtering. The goals are to describe why low-rank models are very useful for collaborative filtering. In case you haven't heard of the term, collaborative filtering refers to when we try to infer the preferences of some users by aggregating data of many users. And this, Amazon does that all the time, Netflix does that all the time, people that show you ads do this all the time. It's really like a very important application nowadays. And low-rank models are actually very, very effective. We will explain how to fit these models to data. And we will take a look at an application to real-world movie rating prediction. All right, so the prerequisites are low-rank models. In the video on low-rank models, we essentially cover the logic behind low-rank models, how to fit them to data when all of the entries of a certain matrix of data are observed. Today we're going to see what happens when some of the entries are missing. But first, let's review very quickly the main ideas from the low-rank model material. So the idea in a low-rank model is that you have data that depends on a small number of factors. Okay. So your data, we denote the data by dij, and what we're saying is that you can kind of express it approximately as a sum of r terms, and each of those terms corresponds to a coefficient that is associated to the columns. In the case of the movies, this would tell us how each movie is associated to each of the r factors. Okay, there's r factors. And then there's another term that's also multiplying that tells us how each of the users are associated to the factors. So if one factor captures, I don't know, superhero movies, this will tell us whether that particular person likes superhero movies or not. Often the factors do not need to be completely interpretable, especially when you have a lot of factors, but that's the intuition, at least. And in fact, we don't need the factors to be necessarily very interpretable if all we want, as is the case for this particular application, is to be able to predict ratings. But I'm getting a little bit ahead of myself. This is a low-rank model. Okay, the rank of L is R. And we saw a few examples about how to use it to model some data. We also saw that the way to fit this model to data is by using the singular value decomposition. Every matrix, because of the spectral theorem, as I show in a separate video, has a singular value decomposition, which is composed of a matrix U that has orthonormal columns, a diagonal matrix, actually I have it here, right? So a matrix U that has orthonormal columns, a matrix S, which is diagonal, and has a number of non-zeros that is equal to the rank of the matrix D. In this case, the matrix D has rank R, we're assuming. But in general, this could be all non-zero. And then we have a matrix of rows that are orthonormal. The singular values are positive real numbers, and usually we order them so that the largest come first. The left singular vectors are orthonormal. These are the columns of this matrix on the left, U. The right singular vectors are also orthonormal. They're the vectors of this matrix on the right, V transpose. Okay, so in order to do low-rank modeling, an interesting interpretation of the singular value decomposition is that it allows us to decompose the matrix into, this could be, so it's a little bit confusing because I just said that D has rank R in the theorem. Here, let's assume that in general, D has rank N1, and we want to do a rank R approximation. Yeah, maybe that was a little bit confusing in the low-rank video. If you got confused by that, I'm sorry. But the point is that now we can think of this guy as basically N1 terms that are multiplying this rank 1 matrix. And these rank 1 matrices we showed in the video on low-rank models are orthogonal if we think of this vector space of matrices. So that basically the coefficient, the singular value is telling us how much each of the terms contribute to the data matrix. So performing a low rank, in order to perform a low rank approximation to approximate the data as a low rank matrix, it's reasonable to just preserve, to just keep the ones that capture the most energy. And that's what we do. Okay, we truncate the singular value decomposition, and that gives us a low rank model. And it turns out that this is optimal, as we show as I'll show in a separate video. We applied this to movie ratings. In the case of these movie ratings, once we subtract the mean, the matrix is approximately rank 1. So we approximate the whole matrix as a rank 1 matrix plus the mean. And this gives a reasonable approximation. And we saw that we could interpret the coefficient in terms of the different movies and different users. So in particular, movies about superheroes had a negative coefficient, and like romantic comedies had a positive coefficient. And this also allowed us to figure out how the different users were associated to this factor. So the users that have a positive value of the right singular vector, the first right singular vector associated to this left singular vector, are going to like romantic movies and not like superhero movies. Okay, and that's indeed the case. Here, these guys like romantic movies, these guys like superhero movies or hate romantic movies. Of course, for realistic cases, you're not going to have a single factor, which is why we want to include R factors. This is why we want to consider a rank R model as opposed to just a rank 1 model. But I think that this simple example kind of captures the point pretty well. So what are we interested in today? We're interested in looking at collaborative filtering, where you try to infer user preferences from other users. If we think of this in matrix terms, we actually want to understand what Molly is going to think about The Dark Knight from different ratings of other people, and also from some of her other ratings. If you don't have her other ratings, this is going to be quite complicated, right? This is known as matrix completion in the literature, because you want to complete a matrix that is incomplete. There are some missing entries. Why should this be possible? Where you can think that if you see that Molly really likes Love Actually, and Bob also likes Love Actually, maybe, this will tell you whether Molly is going to like Pretty Woman or not, depending on what Bob liked. Okay, that's kind of the logic. So that's essentially what's happening when we apply a low rank model to solve this kind of problem. So let's think a little bit. Like matrix completion, the first time you encounter it might seem like a nilpost problem. A nilpost problem is a problem that doesn't have like a solution. It could have like many different solutions that are consistent with the data, so you might not want to worry about it. So here, take a look at this. Okay, like, is it possible to complete this matrix? Yes, I can put in whatever number. I have completed the matrix. I can go home. But if I put just arbitrary numbers, it's going to probably be useless. If I want to do something like predict movie ratings, I should somehow use correlations between users and correlations between movies. In this case, I might want to assume that everyone is super correlated. If everyone is super correlated, how would you fill in this matrix just intuitively? Well, ones, right? Like, for example, here you see these two ones, you see these two ones, so this guy is probably also going to be the same as this, right? Same logic here, you see this and this, so these two guys are also probably going to be ones. Essentially, this, assuming that everything is super correlated, is just saying, let's fit a rank 1 matrix to this data. What about this case? This case is a little bit different than the other. Okay, so imagine that you use the same argument that I was using right now, and you say, okay, like, no worries, I'm gonna just say everything is correlated. Can you complete this matrix? Think about it for a minute. When you go ahead and try to apply the same reasoning I just applied, you're gonna be like, oh, this is very similar to this, so what do I put here? I don't know, because I don't see any entries in this row. In the user movie analogy, there's this person that hasn't rated anything. So how am I gonna know, what coefficient? Like, okay, sure, probably all the ratings are gonna be the same, because this is kind of telling me that all the movies get the same ratings by everyone, but I don't know what rating that is going to be. okay? So if we are missing a whole row or a whole column, that's going to be very problematic, and it makes sense, right? Because we don't know how to calibrate. In order to be able to calibrate a user or a movie, we need some observations about that user or about that movie. So this tells us that the missing entries cannot be all in the same row, all in the same column. They should be kind of spread out. Related to in what cases the problem is well posed or not. Oh, actually, sorry, like just to drive the point home, this is a rank 1 decomposition. The problem is that we just don't see this coefficient because we're not seeing anything in that row, so good luck. Okay, that's the point. I mean, we know this, as I said, but we don't know the coefficient in the column. So in the second row, not in the column, in the second row. Okay, so related to when this matrix completion problem actually makes sense or is well posed, what do you think about this matrix? So now imagine that we pick some entries at random from this matrix. Do you think you're going to be able to complete it? And the answer is that probably most of the entries you will be able to complete. Why? Because you're going to basically see all zeros, and you're just going to complete everything else with zeros, so that things are, in this case, rank 0. It's not the best example maybe, but anyways. Like the lowest, like everything is going to be super correlated. But if you don't see this guy, good luck. So what is the problem here? The problem here is that we have very sparse structure that is not spread out in the matrix, right? So this column and this row is orthogonal to everything else. In a way, if you want to do the analogy with a user, the users and the movies, this is as if you love superhero movies, but when you went to see Superman 2, your girlfriend dumped you right after, or your boyfriend dumped you right after. So you're traumatized and you hate that movie, even though you love all the other superhero movies. So you have like a rating that is very, very special. It's not correlated to anything else. Then obviously we're not going to be able to, without additional information, we're not going to be able to guess that you hate Superman 2. Mathematically, you cannot really compute sparse matrices. In order to, you cannot really complete sparse matrices from some random missing entries. You need the information in the matrices to be spread out. Okay, so now from now on, we will assume that the information that we can retrieve is spread out, because otherwise, what are we going to do? And we're going to take a look at the problem of completing a matrix by fitting a low rank model. So how would you use the SVD to fit a low rank model to this data? You have a problem. The problem is that in order to compute the SVD, you need to see the missing entries, but if you saw the missing entries, then what are we doing here? Okay. So we can be pragmatic, which is often what we do when we're designing machine learning methodology or a statistical methodology. And what we can say is, let's make our best guess for those entries. So we start by centering the data, and then we're going to impute. This is a fancy name for filling in that is used in statistics. I'm going to use it, impute. It's kind of nice. We're going to impute the missing entries. So I'm going to center all the data, and because I don't have any additional information, I'm just going to put in zeros. This is like as if I'm imputing the mean, if you think about it, right? Because if I put the observed mean there and then I center the data, I'm going to get zeros in the entries that we don't see. I'm being very agnostic about these entries. I have no idea what they are. So I'm just going to put in zeros. And now I'm going to fit a low rank model because I think that there's just very few underlying factors. In this case, I think there's just one underlying factor that explains things. So I'm going to fit a rank 1 model to this by computing the SVD of this matrix and just retaining the first term. It turns out that the singular values of this matrix look like this. So this matrix is approximately rank 1, but it's important to point out that because of this imputation business, the rank 1 structure has been slightly damaged, right? Like it's not as clear as when we had all the entries. So these are the singular values when we observe all the entries, and it's much clearer there that you have this rank 1 structure. Okay. So here you see that it's a much more difficult problem now to approximate this data as a rank 1 matrix because we have missing entries. But still, you kind of see it somehow, and we're going to try to exploit it. Okay, so what we're going to do, we're going to add back the mean and just use this rank 1 approximation. And when we do that, this is what we get. Okay, and as I will ask you in the next slide, would you be happy with this? Here I've highlighted in bold the missing entries, and I've put in brackets the actual values. And this is not bad, but you might notice something about all of these values. Think about it for a moment. And think also about why that would make sense. What you might notice is that the values are all kind of closer to the mean that we might want. Like they're, they're not very extreme. Why do you think that happens? It happens because we're imputing the mean. Okay, we put in zeros after centering. So we're kind of imputing the mean in the missing entries, and then we're approximating. So the poor low rank approximation, what is it going to do? It's going to approximate also the mean in those entries. So that's the bad news. Okay, so are we happy with this? Not quite, because we are fitting also the imputed values, and those imputed values, we made them up. So that's not great, right? The good news is that when we look at the estimates, okay, we see that, this guy is closer to 5, this guy is closer to 2. So we have improved the imputed estimates by imposing this rank 1 structure. So if you think a little bit like someone doing machine learning, and if you're a bit pragmatic, what can you do? Well, what you can do is use those imputed values and again impose the rank 1 structure and see if that improves things. And that's actually what we're going to do. Okay, we're going to alternate between imputing and truncating the SVD to try to improve the estimate of the missing entries. Okay, there are other ways of estimating low rank models, of fitting low rank models to matrices with missing entries. This particular example is by Mazumder et al. From 2009. They call it hard impute. There are other ways, so I'd like to just mention a few. Candes and Recht actually prove that minimizing a certain convex norm that promotes low rank structure is optimal in a certain sense. Keshavan et al. Analyze a gradient descent algorithm. So you're doing gradient descent on your factors essentially, and you have to be a little bit clever about it, but it also works well. And then Jane et al. A little bit later showed that you can also do alternating minimization, which means basically that you freeze the column coefficients and then you estimate the row coefficients, which gives you a least squares problem. And then you freeze the row coefficients and you estimate the column coefficients and you alternate on. And that also, and that actually is a very practical way of doing this. So there's many methods for performing matrix completion, and there's a very interesting literature about it, and I encourage you to take a look. But we're going to apply this one. When we do that, we look at the missing entries. You see here that at the beginning they start kind of closer to the mean. The mean is around 3. And as we converge, they converge, that's good news, to something that is farther away from the mean. And we can check that the estimate is actually better. So this is closer to 1. In general, I mean, maybe there are some entries for which it's not. But also realize that the original matrix is not completely rank 1, right? So we have to, not have too many expectations, but the estimates are definitely better than at the beginning. So the iterative procedure actually produces a low rank matrix that is more consistent with the observed entries and gives us a better estimate of the missing ratings. Okay, so we're very happy. I realize here that I cut off diary. Okay, so now let's look at what happens with some real data. I took the movie lens data set. Ideally, I would have done this on the Netflix challenge data, although that's much bigger, so I don't know if I would have had the time to do it. But I think that data is no longer publicly available. You might have heard of the Netflix challenge where they offered $1 million to whoever could predict ratings better. And this actually was a big impulse to this kind of methods. And the methods that actually won, as usual, were a combination of different things, but they had definitely a component that was a low rank model. Okay, and that was around the time where all of these other papers that I showed you came out. So actually these low rank models are very effective in practice. I've also read recently a couple of papers saying that people are trying to apply deep neural networks to this kind of problem, and in many cases they are actually doing worse than the low rank models. which doesn't mean that that is necessarily true in all cases. It just means that it just makes a lot of sense to use low rank models for this particular problem. Anyways, let me stop rambling. Here, what I did is I took the movie lens dataset and I took the 1,000 users and 100 movies with the most ratings. Okay, the observed ratings were 30,000, so there's about 70,000 of them that are missing. And then I extracted a test set and a validation set. We'll see in a moment why the validation set is useful. And our goal is to approximate these 1,000 ratings. Okay, we want to estimate them as well as possible. So in this case, it turns out that so remember that at the beginning we need to do some kind of imputation to get started, like impute, then truncate the SVD, then impute again and so on. To get started, in the simple example, I use the mean rating overall. It turns out that here it works, it's better to use the mean rating per movie. There's less movies than users, so you have like kind of more observations per movie, and that mean is a better value, which makes sense, right? It's a better imputation, and you should use the best imputation you have, right? So that's what we're going to do. We're going to start with the mean rating per movie, and then we're going to alternate between truncating the SVD to a certain value of R, and we'll talk about that in a moment, and reimputing. And in a moment, like we'll talk about it right now. So how would you choose R? So this goes back to the validation set, right? You can do this for different values of R and then take a look at how well you're doing on your validation set. And when we do that, we realize that eventually we overfit, because as you go to higher rank, you have a lot of coefficients, you have a lot of flexibility to fit the training data, but you're not generalizing. You're not learning factors that are actually meaningful in terms of generalization. And the best model turns out to be a model with rank 3. Okay, in this case. Probably, if we had more data, then a higher rank model would be more useful. We're going to evaluate the results looking at the mean square error with the ground truth. So we're going to subtract, take the square, add all the errors up, and then take the square root of that. If we just use the mean per movie, this has a mean squared error of 0.97. Okay, and this is already a pretty reasonable estimate if you think about it. Okay, like how do people that actually have seen this movie like it? That's a pretty good estimate of whether someone else is going to like this movie. Especially because we don't have that many users, so we should expect to improve a lot on this. But we improve on this. Our rank 3 model on the test data, completely held out data, achieves an RMSE of 0.89, so it's doing something non-trivial. It's improving the estimate by, I don't know, 9% or something. And remember that the ratings are from 1 to 5, so, like just to adjust expectations again. So now we get good results, but let's take a look at the factors and see if we can understand a little bit what the model is doing. So now we're going to look at the U1 factor, which associates movies to the U1, left singular vector, which associates movies to the first factor. The highest entries of U1 are Dante's Peak, Volcano, and The Saint. I don't know if you had the pleasure to watch any of these movies. I haven't watched any of this, I think, but I've watched Twister, which I think was like the 4th. And I watched it in the cinema, which shows you how old I am. And it was a horrible movie. It was just like the biggest waste of time ever. And I think I was like 13 when I watched it, and my standards were not very high. So what do these movies have in common? They're very bad movies. And it's not, me saying it. These are the Film Affinity scores. If you look at the IMDb scores, you'll see something similar. Very bad movies. What are the lowest entries? What do you expect to see now in the lowest entries? Well, if these are very bad movies, maybe we'll see really good movies. And that's actually what we see. So this is One Flew Over the Cuckoo's Nest, The Godfather, and Casablanca. Okay, so this factor seems to capture whether you like classic movies that had a lot of critical success. So, One Flew Over the Cuckoo's Nest, 5 Oscars, The Godfather, oops. Here I forgot to, so I will just fill it in. So The Godfather actually has 3 Oscars, and Casablanca has, the Oscars, I'm sleep deprived. So yeah, anyways, the Oscars, I wasn't seeing this, believe it or not. So yeah, so it seems that the first factor captures a contrast between terrible movies that are bad and were actually like a failure, and movies that were extremely successful, both, you know, like from the critics' point of view, but also like, I mean, it would be difficult to find people that didn't like these movies. Although probably in the data set we have some, right, that then love Dante's Peak and Volcano. Okay, so let's take a look at the second factor. In the second factor, I was kind of surprised because Volcano, Evita, okay, I don't know how you pronounce this in American, like Evita, Evita, I don't know, Evita, Dante's Peak, again. So these seem to be quite polarizing movies, Volcano, Dante's Peak, and so on. Again, it seems that these are just bad movies. Evita also doesn't have a very high film affinity rating, although my wife told me she liked the songs. I haven't watched it. Let's see what we find here in the lowest entries. Probably it's not going to be the same kind of movies that we saw in the first factor, because otherwise that would be accounted for by that first factor. And indeed, we see something quite different. We see Titanic, Star Wars, and Raiders of the Lost Ark. So these are movies that are extremely popular, but I wouldn't say that they have had the same critical success as the movies that we saw in the first factor. These were essentially box office super hits, blockbusters, like Titanic and Star Wars were the highest, had the highest box office. How do you call that? Like they made the most money, or they were number one in the box office, or like in history at the time or something. So maybe we could say that this other factor is capturing, maybe, I don't know if I should call it commercial success or maybe popularity. Okay, it's a bit different than the first factor. And then finally, let's take a look at the third factor. And what we see in the third factor is Return of the Jedi, Star Wars, Raiders of the Lost Ark. So again, very popular movies, Star Wars, Indiana Jones. What is going to be the opposite of this? It's not immediately, maybe we'll see terrible movies again. Hopefully not. Hopefully we'll see something more interesting. We do see something more interesting. We see Leaving Las Vegas, Trainspotting, and A Clockwork Orange, which are, you know, like not terrible movies. They're pretty good, in fact. At least, you know, I like Trainspotting, or I liked it when I watched it a long time ago. Here, the contrast is not between good or successful and bad, or a failure. It's more between maybe general public, popular movies, for all publics or something. We say that in Spanish, para todos los públicos, for all publics. That sounds really bad in general public movies, maybe, hopefully. And movies that are edgier, darker, a little bit more alternative. If you've seen any of them, you know, some of them involve drugs or like a little bit of violence. Actually, these two involve drugs heavily. So apparently that's maybe some people don't like it that drugs appear, and that's why they're down rating. I don't know. I want to stress that this is completely data driven. So that's what comes out of the model. It's for this particular 100 movies and this particular 100 users. So it doesn't mean that it should necessarily generalize. Although it's quite plausible that if you like Leaving Las Vegas, you might also have liked Trainspotting, and the same for Star Wars and Return of the Jedi. You know, unless your partner dumped you right after watching the movie or something. Okay, so in some sense, the Return of the Jedi is the opposite of Leaving Las Vegas, at least in this model. I'm not going to show you the coefficients corresponding to users because we don't know these people, but you could go and look, and then essentially what you would see when you look at the coefficients of different people is whether they like this kind of movie, if you look at the entries in V3, or more this kind of movie. Okay, that's what the model is capturing about each user. And if they like, movies of questionable quality, like Dante's Peak or Volcano and so on, or they like blockbusters like Titanic, or they like more like critically acclaimed films like Titanic. That's what the model is capturing completely automatically, which is pretty cool. Again, I want to repeat this thing, which I think I said in the other video, where this interpretability, once you have more and more factors, becomes a little bit more muddled up, because again, it's completely data-driven, and it can be aided if you enforce some structure into the coefficients. For example, in topic modeling, it makes a lot of sense to make these coefficients non-negative, and that's why people apply non-negative matrix factorization in that case. In finance, for example, you want to have sparse factors because maybe you want to invest in a few things that kind of give you a lot of variance. So then that's what sparse PCA is for, which is also a low rank model where you enforce sparsity of the coefficients. So what have we learned? We have learned how to perform matrix completion with low rank models, and we have applied it to some real world movie data. Thank you very much.